far down into the plate the defect is.
Yeah.
I know enough to get me in trouble. I got nothing. You take over. But
Ladies and gentlemen, welcome to Let's Weld Something. I'm going to be your host today, Garrett Vickery. I'm the non-destructive testing instructor here at Cali College. I've got with me
Sean Floatman, or some of you might know me as Dabs Wellington.
and we are taking over the channel today, ladies and gentlemen. What I brought today is a process called phased array ultrasonics. You ever heard of that?
I have. I've never had any first-hand experience, so I'm very excited to be here today.
Fantastic, folks. Hit the comment section. Let us know the inspection processes that you've got experience with. So traditional ultrasonics, okay? We pull sound into a material and interpret the echoes, right? We have one sound crystal, much like this. It's called a transducer, okay? At a fixed angle, we can send sound through that material. Well, with phased array, where we ramp it up, is we have this probe here, which has 64 sound crystals inside of it. Okay, so we are firing multiple sound crystals at different sequences of timing, right? So when I fire one wave, I can fire another one behind it and I can push it. So I can steer and I can focus my beam in order to interrogate certain areas and locations of the weld or the component with a little higher scrutiny.
So is this the same process one would use, say, when you're expecting father? Are we going to know whether or not that this weld is a girl or a boy at the end of the day is what I'm after?
It is the exact same technology.
Okay.
Yeah,
Okay,
absolutely. And the view on the screen here, if you guys can see that, is we call this, actually jokingly in the business, we call this the baby view.
Perfect.
Because if you've seen an ultrasound before,
It looks very familiar.
looks
Yeah.
just like that, right? But to tell it whether it's a boy or a girl, we're mainly telling it whether that weld's got lack of fusion, slag inclusions, porosity, cracks, that kind of stuff.
And how are we going to be able to differentiate between all of those defects on the screen?
We do that via a calibration process and basically it should look like this, but it looks like that.
Now, what are the benefits behind this versus, say, a typical destructive process?
Oh, well, you can save the component. I mean, you don't destroy anything, and we can re-implement the component if it's still usable, or we can identify repair areas so that a technician can go in and make repairs.
So this would be something much more beneficial in the field.
100%.
Yep.
Yes, sir. And in a wide variety of fields. In pipelines, refineries for corrosion mapping is also a process for that. Weld interrogation, you name it. This inspection process is capable.
Very cool.
Good deal. So let's dive right into it. I have a weld here. This is actually an API 1104 test plate that us inspectors, this is a, we have to go through a certification process in order to become certified to do inspections. So when a student comes to Cali College and takes our courses, they're not done yet. I mean, there is time on job that's required, as well as a 3-part certification exam. And what that consists of is a general theory of how the stuff works, a specific test, which is over procedural knowledge and things like that. If this, then what questions. And then a practical exam where they actually have to test a plate or a component that has known flaws in it and locate and record those flaws.
Okay, very cool.
Very cool. So this plate is one of those. It's made by Flawtech. So it has manufactured defects inside of it. There's a book.
And so there will be a map of where those are located, and you have to be able to search and find those out.
Correct.
Awesome.
We have to locate them, name them, and record them on the application.
So not only find them, but be able to differentiate between lack of fusion, inclusions, different things like that.
Yes, sir. And we'll do our best to do that today. I'll show you. So what we're
Well, I
looking.
hope I don't hinder the process, but you know.
We're good to go, folks.
They did invite me for a reason, and I hope I don't disappoint.
Good deal, good deal. So we're looking at our inspection screen here, and what I have is I have sound that is firing in that material from 70 degrees to 40 degrees. So I'm sending sound in, and it's gonna bounce. It's gonna bounce all around inside of that material. So up at the top of this is my sound beam that's traveling at 70 degrees, and down low is the beam that's traveling at 40, and every angle in between.
Okay.
Okay, and when I come onto this material, what we're looking at here, let me turn the gain down just a little bit. Think of gain like volume. Notice the signals get more intense or less intense.
So that's just intensifying the feedback from the radio waves.
Exactly.
Okay.
Yeah. So what we're looking at here, don't worry about that signal there because there's a scratch on my probe wedge here. Notice if I put my finger over it, I can.
So that's probe interference
Yeah.
versus something actually resonating back from the sound.
Correct.
Okay.
We call that non-relevant signals. So we're looking at, I'll show you, I'll point out here what we're looking for. So this signal right here, I want that to remain constant, okay? That signal is the top of my weld, the weld crown, okay? So there are features of the weld that are gonna send sound back that aren't defects necessarily, and as long as those stay put and the sound sees the same things throughout the weld, then we're happy. But as we scan along this material here, we're just gonna slide along. When this signal here is our root signal, okay? So think of it top of the weld, bottom of the weld,
Okay.
right on? And so as I slide here, I'm looking for things to pop up that don't belong there. And I need to put some jelly on the belly because I'm getting sticky. Sorry about that air compressor, it'll scare you on it. And so we're gonna just drag here. And bangarang.
So that would be a defect on the face, correct?
On the, like the weld face, absolutely.
Yeah.
Yeah, and notice I said that this is the bottom and this is the top of the weld. So that's my 70-degree sound wave going in and catching a lack of fusion on the lower, so we've got a double V groove here. So we've got, I'm catching lack of fusion on this lower bevel here.
Okay.
On the nearer side to me.
Okay.
Right on. And I can even put this right here. This is called a gate. And this signal is, notice it's in line, right? So when we can come up top here, see this DA, PA, and SA?
Yep.
So SA is the sound path distance, meaning that's how far the sound traveled before it hit that item.
So you can actually pinpoint how far down into the plate the defect is.
Yeah, absolutely. And PA is the projected distance along the surface. So if I were to take a tape or a caliper from the front face of my transducer here, that defect is 0.174 inches ahead of me.
Okay.
And it is 0.649 inches down.
So I mean, you zeroed directly into the
We got
defect at that point.
Absolutely.
Yeah, there's no guessing game there.
No guessing game there. And so where, again, this steps up from traditional ultrasonics is with traditional ultrasonics, all I have is this screen with the squiggly lines. I don't get the weld map. I don't get the color scale.
It's like the difference between 2D and 3D at that point.
Exactly, yeah. And it's easier to digest that information, especially if you're telling a refinery or a company that their $500,000 component is bad and they ask why, and you say, well, because that squiggly line said so.
Now, since we're on this side, and you've got a defect here, you flipped and shot it from the opposite direction,
Let's do it.
would we be able to pick up the same defect?
Lack of
If-
fusion can get tricky.
As long as there's lack of fusion through the entire root of the weld.
Yes, and there
Since that
she
was
is.
multiple passes, there could be lack of fusion between the second and third. So
Correct, yeah.
You're not entirely sure at this point where and how far the problem goes down into the root.
Absolutely. We do want to interrogate from both sides because the signal, depending on what kind of flaw it would be, would look different from one side as opposed to the other. Think of like slag inclusion, which could be chunky or shaped anything, right? From one side, it could have ripples like this, and from another side, it could be flat. And so on the flat side of that, it could look like a crack. But if I come over to the other side and I see signals that are dancing, that's not a crack.
Okay.
Okay. Think of like waves as they come back from an ocean, right? If the beach front is flat, the waves go back flat. If the beach front is rocky, then the wave comes back all sooner or later.
So the waves will be broken periodically and
Absolutely, and that's what we're seeing with the squiggly line on the screen there. We call that an A scan, we call this an S scan. And so we can keep going, there's our lack of fusion, okay? And we can keep rolling, nothing too crazy, nothing yet. Just some signals from the weld geometry. And I'm not a huge fan of that popping up right here. Okay, remember I said
yeah,
that.
because that one's been constant the whole time.
Let's see if we can get it there. that right next to this one right here. Right next to bottom of the weld, top of the weld, so it's right next to the top of the weld there. I am gonna try and zero in on her there. It's all about contact. If you don't have good contact, then the sound won't go into the material. And boom, there you go.
Yep, so that big red spot there is directly correlated to that huge spike then. Yep.
And I can tell you that it's 0.077. Remember I said it's towards the top, right? Top of the weld down low, bottom of the weld up high. 0.77 inches from the top down, and it's 0.7 inches ahead of me. So it's probably in the middle somewhere. And with a signal that high and that, like if I kind of like interrogate it a little bit, notice it's just one. I don't really have multiple spikes. That's could be an inline crack, like a centerline crack.
Okay. Yeah, you can't argue with that.
It's complex, man. It takes a lot of time and a lot of effort and a lot of grasping of the physics of it all. But also, the reason why I love NDT is because we hard hat and steel toe boots just like the rest of them, and we're involved in getting technical and hands-on.
Well, it's a non-destructive peephole into the weld. You know, that's pretty awesome.
Absolutely. I like to tell folks we're the chain link between the welders and the engineers, because we have to be able to be successful in communicating with the welder what we're seeing and where they need to repair. And we also need to be successful in communicating with the engineering staff on what they expect out of the material and how things should go. Good deal. It's been great having you and a great time down here with Let's Weld Something. Thanks for letting me take over for the day. Don't forget to hit that subscribe button. Give us a thumbs up. Hit the comment section with any inspection experience that you have, either being inspected, or doing inspections. We'll catch you next time.
Thanks for hanging out. Play the defect is.
I know enough to get me in trouble.